This example of centripetal force is quite a bit different than the first one because our car is turning around a banked corner, which means the surface isn't flat. The road is actually a little bit curved, which means that there's an angle that we have to somehow take into account here. And we can see that because the angle is written in the question as 19 degrees. So we need to do something with this 19-degree angle. So we should kind of determine what force provides the centripetal acceleration. So because of the angle, right, the cause of the centripetal acceleration is the horizontal component of the normal force. So to simply answer A, the horizontal component of the normal force is going to be Fn sine theta. And that will come into play a little bit more as we see what a free body diagram looks like. So if you're still not convinced, you can draw a free body diagram. And we'll see here that we have our road, or not really a road. Our road is actually going to be the incline here. This is 19 degrees. So our car is somewhere on our road like this. We have FG. And of course, we have our vertical or parallel and perpendicular components. And then Fn is going to be perpendicular to the surface as usual, which means that we have a horizontal and a vertical component to deal with. And I'll do these in different colors here. So we have a horizontal component, which is going to be like this, and then a vertical component, which is going to be like this. And those are the values that we are going to deal with. So we have our angle 19, which is also the same angle in here, which is going to be the same angle up here. All of those angles are 19 degrees. And this helps us with our math. It's a little bit easier this way than having to calculate some unknown angle. So let's draw, or we've drawn our free body diagram. So what constant speed must the car travel to make it safely around the curve? So note that the vertical components here of your forces add up to 0. So that means that F net equals 0, which means F net, actually there's no vector here, equals 0. And so 0 equals your force, your normal force, times cos theta, that's the vertical component, minus Fg, uh, which is just going straight down. So we're not going to need to make use of the parallel or perpendicular components of Fg for this question. This then can tell us that Fn cos theta is equal to Fg, which now allows us to solve a little bit more because we know what Fg equals. So we know that Fg equals mg, and then we can rearrange a little bit more to solve that Fn equals mg over cos theta. So we can now start to plug in some information. 1100 kilograms, 9.8 newtons per kilogram, divided by cos 19. This is going to give us a normal force of 11,401.15 newtons, and we'll leave that number there unrounded because we're going to have to make use of this for the second part. So what's the speed? Well, for our speed, we're going to look at the x component of our normal force. So we know that the sum of all the forces in the x direction are equal to ma, but a is the centripetal acceleration, so it's no longer ma, it's mac. We can sub in the only x force that we're going to deal with, which is your Fn sine theta. And instead of mac, we have m, ac is v squared over r. We can do a little bit of algebra to rearrange this to solve for our v. And that's equal to our Fn, 11,401.15 newtons, times sine 19, times 85 meters, divided by 1,100 kilograms. And when you take the square root of all of that, you're left with 16.94 meters per second. However, because we're talking about a car, it might make more sense to round and convert this to 61 kilometers per hour.